Alright, here again we have the Pythagorean Theorem, which again, it works only in right triangles, and it says that the leg squared plus the leg squared equals the hypotenuse squared. We write that a squared plus b squared equals c squared. A and b are the legs, and c is the hypotenuse. Let's use it on this example down here. Find the length of the missing side. Leave your answer in simplest radical form if necessary. Okay. So we write down the Pythagorean theorem is that a squared plus b squared equals c squared. Make sure you get the right parts in the right place. It does matter. So let's identify our hypotenuse is the longest side, the one across from the right angle. So here's our hypotenuse. And then we have a leg and a leg. Okay, so we want to go leg squared plus leg squared. Well, we don't know that leg, so we just call it a. So a squared plus the other leg was length 6 squared equals the hypotenuse squared. Let's do our squaring. 6 times 6 is 36, and 10 times 10 is 100. We're going to solve for a. We subtract 36 from both sides to get a by itself. When I do that, I get that a squared equals 64. And then to remove a square, you take the square root. The square root of 64 is a whole number, so we don't have to leave it in radical form. The square root of 64 is 8. So my missing side was length 8. Alright, so here again we're asked to use the Pythagorean theorem to find the value of x and leave our answer in simplest radical form. So again, we start with the Pythagorean theorem, a squared plus b squared equals c squared. Carefully place our numbers. Our legs are x. So we have x squared plus the other leg is 5. Those are the two attached to the right angle. Equals the hypotenuse, that longest side, 10 squared. Okay, let's do our squaring. So we have x squared plus 5 squared. 5 times 5 is 25 equals 100. We need to get x by itself, so I'd have to subtract 25 from both sides. That gives me x squared equals 75, and I take the square root of both sides. Now, if you put that into your calculator and try to find the square root of 75, you'll notice that you do not get a whole number. You get a decimal that just continues on and on and on. So that's again where the simplest radical form comes into play. They want us, if it's not a whole number, to leave it with a radical, but simplify it as much as we possibly can. So again, hopefully you've written down in your notes those perfect squares, at least the first set of them. Those are numbers that have whole number square roots. So for example, 4, because its square root is 2. 9, because its square root is 3. 16, square root is 4. 25 has a square root of 5. 36 has a square root of 6. 49 has a square root of 7. 64 has a square root of 8. 81 has a square root of 9. 100 has a square root of 10. 121 has a square root of 11. And 144 has a square root of 12. These would be good to have in your notes. Again, they're called perfect squares, and they're called that because they actually have whole number square roots. And when we're trying to write in simplest radical form, what we want to do is look at the number that's left in the radical and say, okay, can we rewrite it using multiplication as factors? Do any of these divide evenly into 75? Well, 25 does, and we rewrite it as that. 25 goes into 75 3 times. So we can rewrite 75 as 25 times 3. Go ahead and check that. 25 times 3 is 75. The next thing we do is we want to separate those into two separate radicals, which you can do when you have multiplication, not with addition, but with a multiplication. So that we have the one in front that does have a whole number square root and the one behind that does not. 25 has a square root. Its square root is 5, so we go ahead and do that and remove the radical. 3 does not have a whole number square root, so it has to stay in the radical. And our answer, simplified in radical form, is 5 times the square root of 3.